Our next topic is directed acyclic graphs, or DAGs, which you may have seen before. And they're just a way to encode independence assumptions. It's like a quick way to show what you think is independent in a joint distribution of several random variables. So we'll see what I mean. Last time we saw that you can write a joint distribution or a data generating process as a set of structural equations, which is essentially just specifying. All you're doing is, instead of writing out the joint distribution as one big density, you're saying what the different pieces of it are. So because you can factorize a joint density into the product of conditional and marginal densities, you can describe that joint density completely by just saying what are those different pieces of it. So in this case, we have a joint density where the different pieces are this. So I know that the marginal distribution of z is uniform. I know that the distribution of x given z is this, and the distribution of y given z is that. So when I write this down, I've implied that my distribution factors into the product of these three distributions, this marginal and these two conditional distributions. So I can write that. I can just kind of put little circles around these different equations, and I can do them like this. So here, what I'm showing by the arrows, when I put an arrow between a box and another, is I'm showing that the thing at the butt of the arrow and the thing at the point of the arrow, whatever that thing is at the butt of the arrow, is going into the definition of the distribution of the variable that's at the point of the arrow. So here I have x is Bernoulli, but my probability is dependent on z. So that's why I have this arrow coming from z. So z is feeding into what the distribution of x is. Similarly here, z is feeding into the distribution of what y is. But x does not feed into y because the distribution of y does not depend on what x is. Or at least the way that I've written it here doesn't. And that's basically all that a DAG is. It's just a way of writing a probability distribution, showing kind of what variables feed into the conditional distributions of others. So all we're doing when you see a DAG is you're specifying what the factors are. So I have this generic distribution. If I have this DAG representing it, I know that this here is the density for a normal with mean z. That's what we have here. This thing is the density for a Bernoulli random variable with probability. This is a thing called the logistic function. We'll learn about that in a second, actually. Logistic function of z. And then this thing, this factor of the distribution is just a uniform over 0, 1. And in fact, by this here, the density for y actually doesn't depend on x. So we also know that this part here, we don't even need this x here. Or the dependence on x is 0, right? This function doesn't vary with x. So again, maybe you already get it, but I'll just show you. If you have a factorization like this, how can you build a DAG? Okay. So we start with the marginal distribution and we draw a node. Say this is z. Now we go to the next factor, and we look at what is the variable that we are conditioning, and we see what it's being conditioned on. So x is being conditioned on z. That means I need an arrow from z into x. Now I go to the next factor, and that's y. And here I have y being introduced, and y is being conditioned on x and z. So I draw y, and then I need arrows coming from both x and z into y. So let's just practice the concepts here. And again, there's no mathematical. Well, we'll see. DAGs are useful in a second, but at this point, all I want you to understand is that it's just a kind of very quick graphical way where you can look at something and know how a density factors. It's almost like a nice notational convenience, right? I don't even need to specify what the distributions are of everything. If I'm just interested in knowing what's independent, what's conditionally independent, that's the point of DAGs, to see it in a kind of visual way. There's no it's not like a formal mathematical tool. It can be used that way, and we'll see that in a second, but really all we're doing is reading off conditional independences and marginal independences. So let's practice building one. Let's say I have a joint density and I tell you that it factors in this way. Okay, I can write this as a product of these different functions where this thing is a function of x, z, and w that happens to be, if I fix for any value z and w and I integrate over x, the value is 1, so it's a conditional density of x, and so on. So if I can write it this way, then let's draw a DAG. So we start from the marginal density, so I'll draw w here. And w is not being conditioned on anything, so we're good. Now we go to the next one, we have z, so I add z. Z is not being conditioned on anything, so we're good. Now we go to the next one, I'm adding y. Y is being conditioned on z, so I need to draw an arrow from z to y. And now lastly we have x, and x is being conditioned on z and w. So this is our DAG. And I could have gone the other way. I could have given you this DAG, and I could have asked you to write how this joint density factors, and you would have done the same process in reverse. You would have started with things that have no arrows going into them and said, okay, well, those are going to be our marginal distributions, and then add in, for each node, basically add in the factor that corresponds to it, which is the thing where you put that variable as the thing being conditioned on, and you put everything that's going into it as the conditioning variables. So here's something that's interesting. The factors are not unique, right? We already saw, again, in the previous lecture, that it doesn't really matter. It's not like it doesn't really matter. It just doesn't matter which way we factorize this joint distribution. I could write it like this as a function of z times the conditional density of x given z times the conditional density of x and z, whatever. Or I could start by having the marginal of y and then the conditional density of x given y, and so on and so forth. And again, this is, if you've forgotten why this makes sense, I think it's easiest to see by just looking at the definitions of conditional probability. So the probability of y given x is let's even just go to counts, okay? So the definition of the proportion of times that y happens when x happens is the same as how many times is y happening at the same time as x relative to how many times is x happening, right? And also I can ask the other question, which is the proportion of times that x happens when y happens, and that's this count over this count. I notice that this is the same as this, right? And so I can multiply my count of y over to the other side on that one, and my count of x over to the other side on that one. So here I have a count of x, and here I have a count of y. And now these are the same number, right? So that means that these two things are this is the same number as that, right? And this is exactly this kind of factorization, right? This joint distribution, or count of two things happening at the same time. I can write that as either the product of the marginal of x times the conditional of y given x, or I can write that as the product of the marginal of y times the conditional of x given y. It doesn't matter. It's just I'm this count here, I'm just counting up how many times do these two things happen at the same time, which I can get by either first counting how many times does y happen, and then saying, okay, what fraction of those, what I need to multiply that by some fraction of times where x happens. Or I can first count x and say multiply that by some fraction of times where y is also happening, right? So it doesn't kind of matter. It doesn't matter which one, which order I do that in, or what I count first and then what I multiply by. So this what I'm showing you up here, which we went over last lecture, is a generalization of that idea. And you can do that for multiple random variables. And so I can just factor these things in a different way. So you might hear a mathematician say the factorization is not unique. And what that implies with what we're talking about now with DAGs is that DAGs are also not actually unique. So this distribution, this joint distribution, if I don't know anything, if all I know is that I can, the generic stuff, here I haven't assumed any independence or anything, right? Because I can always factor any joint distribution like this. I haven't said, oh, actually this thing doesn't, if I already know Z, then I can get rid of X here. But in general, I could, the DAG that represents this factorization is this, right? So here we have Z going into X, X going into Y, Z going into Y. That's this. The DAG that represents this situation is different because here we have start with Y, and then we have arrows going into X and Z, and then X into Z. So we actually have different DAGs, two different DAGs that represent the same potentially joint distribution. So this is important to understand because you can draw a DAG where the arrows don't imply causal relationships, okay? The DAG is really just telling you about what is independent, what is conditionally independent. We're going to see how to figure that out from the DAG in a second. But before we even get there, I think a lot of people see DAGs and say and immediately assume, okay, well this means that Z causes X, and then X causes Y, and Z is also has an impact on Y. And generally, I mean, intuitively you can read them like that, but it's important to understand that really what this is saying is that this joint distribution can factor this way, but if I don't know anything else about it, then this joint distribution can also factor that way over here. So, this is just describing some relationship between the variables, patterns between the variables, nothing about causality, okay? So, let's talk about how you can actually read what's independent and what's dependent from DAGs. So let's look at this DAG, which covers 5 variables. So we could imagine we have some joint density over X or YX, M, R, and L. And if I'm looking at this DAG, I can write out all the factors that correspond to each node. So I have L and R are marginal, and then M has L and R going into it. So I have to condition on L and R, and so on and so forth. So this is the distribution, this is the factorization that I get. And I know that I can always write this distribution a different way, right? Which is that I can write Y given X, M, R, L times X given M, R, L. So this is our generic factorization times F given F of M given RL times F of... Okay, so because I have this factorization, and now I'm telling you that I also have this factorization down here. So this is something interesting because from this, you might say, well, these two factors, these are the same, right? So I can get rid of those, and these two are the same. So let's get rid of those. So you might kind of start to see that, and here L and R are being conditioned on. So these things don't, these densities do not impact these marginals. So you can actually, start to see like, okay, actually, this has to be equal to this, which means that R and L are independent, right? So that's what's being said here. And you may also see that M and X are independent conditional on L. That's a little bit harder to see, but you can start. Again, this is not rigorous, so don't take this super literally. But by looking at a DAG, just the factorizations, you can kind of start to see these things. Some of these things are more obvious, right? Like so that L and R are independent. Given that this DAG is the case, that might be kind of intuitive to you. Some other things may not be. So I'll show you a picture of that. So here, my question is, are X and Y independent? Are L and Y independent, conditional on M? Those things are not going to be super obvious. I mean, you could try to do some math and integrate, and you can always show whether you can always try to show it just directly from the factorization, but it's not always easy and not always totally obvious. But what we're going to see now is that there's actually a game that you can play just by looking at this picture that will answer all of these questions pretty easily, as long as you know how to play this game. So here's the game. This game is called D-Separation, and I think it's pretty fun. Hopefully you do too. So the game is like this. The rule is that two variables are independent if all paths between them are blocked. We're going to describe what paths are and what blocking is in a second. So path is a traversal of the DAG, ignoring the directions that the arrows point. So if I'm talking about a path between y and x, I just need to follow the lines between y and x to get from one to the other. So here I can go from y to r, r to m, m to l, l to x. So the path does not care which way the arrows point. Now, we also talked about blocking, and a path can be blocked by something called a collider. A collider is a node along the path where the arrows on the path going into the node point into each other. So in this example, M is a collider, because if you look at this path, it goes into M via this arrow that's pointing into M, but then it goes out of M via this arrow that's also pointing into M. So that is the definition of a collider. It's a variable that has two arrows pointing into it, where the path follows one arrow in and takes the other arrow out. If you have this situation where your path is going through a collider, the collider blocks the path. So I've colored it here in red to illustrate that. So intuitively, you can think of a path is something that allows information to flow from one variable to another, or where if you know something about y, and there's a path from x to y, then knowing something about y can tell you something about x. If you have a collider, however, along that path, the flow of information is blocked. And so that information about y that otherwise would have been useful for x, you now don't have it. And like we said in the very beginning of this section, variables are independent if you can't get information from one to the other. Something to know about colliders is that whether or not a variable is a collider depends on the path that you're looking at. So for example, let's just think about m and y. If we're talking about a path from y to m is not a collider here because, well, one, it's not between m and y, it's at the end. But two, the path is not going out of this arrow. So it depends on what path you're looking at. So a more clear example might be if you had another variable here, let's say this were called z, and we were looking at the this path here where this continues to z. M is not a collider for this path. M is a collider for the other path that we were looking at, right? That goes like this. Because here, that path goes through this arrow and then out that other arrow that's pointing opposite direction. But for here, since the arrow points out of M is not functioning as a collider there. So it's not just that the node has two arrows pointing into it, it's that the path has to be going in one arrow and then out that other arrow that's pointing in the opposite direction. That's what makes it a collider relative to that path. So given that, we can immediately read off all of these independencies. Why? Let's just look at x and y. So x is independent of y because we need to say this, we need to essentially ensure that all paths between x and y are blocked. There's only one path from x to y. It's this one, right? And it's blocked by m. We already saw that m is a collider in this DAG on any paths that go through it, right? Because if you're going through, you have to be going in one arrow and out the other, pointing the other direction. So m is a collider for all paths that go through m on this DAG, which basically tells you that anything that's on one side of m is independent from anything that's on the other side of m. So we know this immediately, all of these. So this game, by the way, the relationship between this kind of like visual deseparation game that you can play and these formal independence assumptions, which again tell you something about how you can factorize the joint density. This was mathematically proved in the late 80s, mainly this dude called Judea Pearl, who's still around. and he's done a lot of work in causality and computer science. He's an interesting guy to know about, at least. So we've known this for a while. Now, what about conditional independence? Turns out you can also play this game. We just need to complicate it a little bit to account for conditional independence. But it's the same basic idea. We say that two variables are conditionally independent if all paths between them are blocked. That's the same. The only thing that changes is the rules for what's blocking things. So for marginal independence, the only way to block a path is with a collider. For conditional independence, you can also block a path by conditioning on a variable, unless the variable you're conditioning on is a collider for that path, in which case it unblocks the path. So you can think of the way that I think of it is like conditioning. By conditioning on a particular variable, it kind of switches the polarity of that variable. So if that variable was previously something you could pass through along a path, now it's blocked. If that variable was previously something that was blocking the path, now it's not blocking. So here's an example. We can ask about whether y and x are independent conditioned on r. So there's only one path between x and y. It's this one, right? We draw it. Now we just want to know, is it blocked? Well, we know m is a collider. So m is already blocking, right? And now r, since we're conditioning on it, is also blocked. So the path is doubly blocked, which means it's blocked. So all paths between x and y are blocked. Therefore this conditional independence holds. Notice I could have also conditioned on L as well. I could condition on both of them, which I don't think we mentioned when we were talking about conditional independencies, but there's no reason why you cannot condition on multiple things at the same time. In these definitions, it's just the same, just the same as saying y and x are independent in every strata of R. We can say y and x are independent in every strata of defined by R and L. Okay. So what about this one? Let's look at asking whether y is independent of x given m, or we know we're in a particular stratum of m. So here we can draw our path, and we know m is a collider, so it's originally blocked. But now we're also conditioning on it, so that actually unblocks it, and now information can get through. So y in this DAG, y is independent of x marginally. But if I condition on m, it's actually no longer independent. So that's actually quite an interesting result. And intuitively, the result is this, right? So if I don't know what m is, knowing y doesn't tell me anything about x, because the information from R, if you think about the factorization, right? R is kind of determining the values of y, and R is determining the values of m, or the values of m are being determined by both R and L, and the values of x are being determined, by L. And so if I don't know m, right, there's nothing that y can tell me about x, because I think it helps to think about the code, right? If I first am generating R and then generating L, then I generate m, both based on R and L, and then I generate y. There's nothing here that's possibly telling me about what the value of x is. If I know m, it changes, because m actually tells me something. If I know y and m, that actually tells me something about what L was. Or in a substratum of m, that gives me, since I know this, that tells me information about what both L was and what both R was, right? And then if I additionally know y, that gives me more information about R. And so that means that L had to be something else, which gives me information about x. So I'll give you a simple example. That's probably not clear at all. So don't worry if it's not making sense. Let me give you a simple example here where these things are actually, so here's like uniform, let's say 0, 1, uniform 0, 1. Okay, and here's a simple example. X is equal to L, Y is equal to R. So this is just passing the information straight through. There's no additional randomness in Y and X. And then here m is equal to r plus L. Okay, so let's draw some random numbers. So here, let's say I get 0.1, and then here I get 0.7. That means that this is 0.7 and this is 0.1, and then the sum of the two is 0.8. So question is, if all I tell you is that this is 0.1, how could you possibly know that this is 0.7? You can't, right? However, if I tell you this is 0.1, and then I tell you this is 0.8, well, okay, if this is 0.1, then I know, if I know this, then let's say I didn't know this originally, right? If I know this, now I know that this is 0.1, right? Because I know these are the same. And now here, this tells me, since m is r plus L, and r is 0.1, m is 0.8, so I've conditioned on m, so I know this now, then that tells me that this number here had to be 0.7, and since I know this is the same as that, then this is 0.7. So I've actually managed to get that information through from here to here by additionally knowing what stratum of m we're in. Maybe that made it clear. I'm trying to give you some intuition as to why this kind of game actually tells you something about these conditional independencies in terms of being able to guess what one value is given others. But at the end of the day, I just want you to be able to play the game, basically, and tell me what's independent of other things given the DAG, and understand what the DAG means conceptually in terms of factorization of probability distributions. So to that end, let's play the game. We have this DAG, so pause this video and answer these questions here. So first, are W and Z independent? So we have to find all the paths between W and Z. In this case, there's only one. It's this. There's no collider on the path between W and Z. So information can traverse between W and Z, which means that they're not independent. Knowing one will give me information about the other. Are X and Y independent? So there's only one path between X and Y. It does go through this collider, Z, which blocks the path. So I can't get information through. They're independent. Similarly with Y and W, it's the same path, just goes a little longer, but it's still blocked, right? Conditionally independent given Z and X. Okay, so there's this path. This is the path with no conditioning, right? Now I'm conditioning on both Z and X. So if I condition on Z, that unblocks this. But now I condition on X, which blocks here. So indeed, there's no way to get information through. And these are still independent in this conditioning scenario. All right. Circling back to the top of this section, who cares? The idea of DAGs is just to represent in a very compact, visually appealing way the assumptions about what is independent to what, and under what conditioning scenario is it independent. And right now we're just talking about independence as a way to like describe a population, describe the relationships between variables in a population. But we're going to see in the second part of the course, this becomes super, super important when we start talking about regression and causal effects. And we'll have a little bit more about that at the end of this lecture.